So example 1, we're going to look now at a very theory-based functions question. So this very much sits in the function sphere. We have a diagram here on the right which shows us our y equals f of x, and we're told that the function f is defined as f of x equals x squared times the natural log of x. So this is something we're probably not hugely familiar with. If I asked you what shape that is, you mightn't be able to tell me. But that's okay. Working with an unfamiliar function is absolutely fine. So just to make life easier, I'm going to write that as f of x is equal to x squared times the natural log of x. And we're told that x is an element of OR and x must be greater than 0. So we can even see in the diagram on the right that we only have the positive x-axis there. So that can be important, the fact that x has to be greater than 0. So the diagram on the right shows part of the graph of f. State whether or not f is injective, give reason for your answer. So the easiest way to do this is with the horizontal line test, and that means if I draw a horizontal line, and I'll draw one in here to show you, this should touch the graph at most once. And here it touches it twice, so it's not injective. So just make sure you actually answer the question. I often see students here explain it, but actually forget to answer whether it is injective or not. Not injective, and I will say it fails the horizontal line test. And remember that there is a horizontal line test for both injective and surjective, so you need to go deeper and explain it and test for injectivity, and I'll explain, i.e. a horizontal line drawn, touches the graph more than once. That's enough. More than once. And just make sure if you are using that horizontal line test, you show the horizontal line on the diagram. So part B, find f dash of x, the first derivative of f of x. So this is an interesting part because often when we see questions like this, we lose track of how to actually differentiate it. So let's take our f of x here for a second. We have x squared times the natural log of x. This is actually the product rule, and the reason it's the product rule is we have two functions, so two ideas in terms of x, which are multiplied by each other. So there's my u and there's my v. So I'm going to have to use that product rule. So that's easy to miss, so just be so careful. So I start with my u, which is x squared, and I differentiate it. So du dx, and that gives me 2x. I start with my v, which is the natural log of x. Go to your log tables if you need to, if you don't know how to differentiate the natural log of x. It's 1 over x. Don't assume that everything is bring down the power. Take 1 away from the power, because it's not. So then to actually differentiate that, it is u, so x squared, times dv dx, so 1 over x, plus v, which is the natural log of x, times du dx, which is 2x. Now the multiplication here with the natural log of x and 2x, just be careful. So I have x squared on top and x on the bottom, so x divides into x squared x times, so I get x plus. Now that 2x is multiplied by the whole of the natural log of x, so we're going to write that as 2x natural log of x. So just be careful. Sometimes I see students multiplying what's in the log by what's outside it, and that's not correct. So we're leaving it as 2x, allow that to come forward. Same way if we're multiplying number by a letter, we tend to put the number in front. So natural log by another term, we're making sure that the other piece is in front. So part C, which is utilising part B, asks us to find the coordinates of the local minimum point of the graph of f in terms of E. So how we get the local min or the local max turning points, we're going to let f dash of x, the first derivative, equal to 0. So remember that our f dash of x from part B was x plus 2x natural log of x. which means we're trying to solve x plus 2x, natural log of x, equal to 0. So the first thing I'm going to do is I'm going to bring the x over, so take away an x from both sides, then I'm going to divide both sides by 2x. Now, usually we wouldn't divide by a variable like x, we would keep it, but we only want one particular answer here, so we're not going to lose an answer as such, so it's not a huge issue. So we end up with the natural log of x equals minus a half. So now I want to work out what x is, so I'm going to convert this log. So this is, remember, log to base e of x is equal to minus a half. So whatever way you have of working that or converting that, what I do is I'm going to take the e to the power of both sides. E to the natural log is basically gives me just what's in the log, so they undo each other, leaving me simply with x equals e to the power of minus a half. Now they do want it in terms of e, but we don't want to leave our power as a negative power, so we do want to tidy that up. Also, they ask for the point, so we need to work out the y coordinate as well. You can tidy this up first, or you can sub it in as is. I'm going to sub it in as it is and then tidy it up at the end. So to get my y, I go back to my original function, and that is x squared, so e to the power of minus a half squared times the natural log of e to the power of minus a half. Now you can use your calculator to help with this, but they do want it in terms of e. So I'm going to use my rules of indices. So e to the power of minus half to the power of 2, that gives me e to the power of minus 1. Natural log of e to the power of minus a half. If you look in your log tables and we look at the rules of logs, on page 21, what you're going to find is there's actually a little rule there that will help with that. And remember again, just to show you that this natural log is log to base e of e to the power of minus a half. And that will give us, according to the log table, simply the power, which is minus a half. So here we multiply by minus a half. So tidying that up, that's minus e to the power of minus 1 over 2. So my point has an x coordinate and a y coordinate, but I want to tidy that up. So my e to the power of minus a half, I can bring that e under the line. So that's 1 over e to the power of a half. It means that my power becomes positive. And then power of a half is the square root. So I have 1 over square root of e. For my y value here, the minus stays. Again, I can bring that e under the line, so 1 over 2e. So therefore, my minimum point, my minimum turning point here, or local min point, is 1 over root e minus 1 over 2e. So part D asks, under what conditions is f bijective? So what they're really asking is, for what domain and codomain does f meet this criteria? So first thing we're going to do is break down the idea of bijective. So bijective means it's both injective, which we already answered in part A that it wasn't, and surjective. Now what surjective means is all the possible y values are being used. So what we want to do is limit the codomain so that only the y values we're using are allowed to be used, and that allows us to have the codomain equal to the range, and then it is surjective. So we're going to work them one at a time. Now, the way that this question was asked was really important, because the fact that they asked us for the turning point, when we're looking at limiting or restricting the domain and codomain, that turning point, be it a minimum or a maximum, is really, really important, because what it allows us to do, it allows us to cut the graph at the point where the horizontal line test for injectivity is failing. So what I mean by that is, if we cut the graph here, right, so ignore everything before that point, no longer do we end up with an issue about injectivity, because now after it's turned, the horizontal line test will only ever touch the graph once. So that turning point will always be important for us. It also gives us then the y value, i.e. the codomain that we want. So for injective injective and surjective, i.e. to be bijective, we want to have the x value that is greater than or equal to 1 over the square root of e, and we want to have the y value that's greater than or equal to minus 1 over 2e. Now, another way we could write that is with our brackets. So if we want to include it, we put a square brackets. That's 1 over root e, and then comma, and it goes to infinity. And same thing here. So square bracket means it's included, and then infinity. So this is really the domain, and that's the domain restriction, and this is the codomain. So once we've restricted and say actually we don't care about anything below that red dotted line and to the left of the vertical dotted line, then we're left with just a curve that is both injective and surjective and is therefore bijective. So now let's look at an exponential functions question which includes calculus. So this is a great question to look at from the point of view of a question that may at first glance look incredibly difficult, but the first half of this question is so straightforward. When we look at this question, we're talking about how the exponential function is represented in a real world way. So let's go through this. When a heavy chain hangs freely under the effect of gravity and is supported only at each end, the shape of the chain is called a cantenary, as shown. Using a suitable choice of coordinates, the equation of a cantenary can be written as y is equal to a over 2 bracket e to the power of x over a plus e to the power of minus x over a, where a is a constant. To demonstrate this, a heavy chain is let hang freely between 2 points P and Q on opposite walls on level ground. The coordinates P and Q are minus 2k, which is shown in the diagram, and 4l, which is on the diagram, respectively, where k and l are constants. Both x and y are in meters. So there's a huge amount going on here. But what they've done, I suppose what we need to focus on are two things. So the first is the formula, and the second is the diagram that is using a coordinate grid, even though that grid is not there. So part 1 asks us, given that the point or 0, 2 lies on the path of the chain, show that the value of a is 2. So anytime we know that a point is on a function or on a line or on a circle, we sub it in. So we have or is 0, 2. This represents x and this represents our y. So going with our formula, y, well actually I'm going to go straight to sub in because I have a huge amount of space. So instead of y I'm putting in 2. A over 2 bracket e to the power of 0 over a, which I don't know, plus e to the power of minus 0 over a. Now, 0 divided by anything is still 0, and e to the power of 0, so I have a, so 2 equals a over 2. This all breaks down to e to the power of 0 plus e to the power of 0. But anything to the power of 0 is still 1. So what this does is it becomes 1 plus 1. So it doesn't matter that there's still an a in that power because 0 divided by a is still 0. So when we work that through, we end up with 2 is equal to a over 2 times 2, which just gives us 2 is equal to a, because 2 on the top and 2 on the bottom cancel each other out. This is exactly what we want, QED. So all that was required here was actually some substitution. Part 2 of this says, find the height of the chain above ground level when the value of the x coordinate is 3. So now what we're going to do, having the equation, or sorry, having the function, but also knowing that a is 2, we're going to sub in x equals 3 and work out y. So y is equal to 2 over 2 bracket e to the power of 3 over 2 plus e to the power of minus 3 over 2. Now, 2 over 2, that will simplify to give me 1, but this can go straight into the calculator. Just remember that they've asked this correct to 1 decimal place. And when we put that into the calculator, we get 4.7. Just a little tip when we're working, a little bit of a tip when we're working with our e's, just a lot of practice putting those into the calculator, and because they are quite time consuming, make sure you know where that E button is on your calculator. E is Euler's number, so it stands for 2.718. So just get very good at that. Just be very careful when putting this in that you come out of your power before starting the second E. So part 3 is find k, the value of the y coordinate, in terms of e. So here we're being asked in terms of e. Now, for p, here's my point p. I know my x, and again, I'm looking for my y. So it's pretty much the same question, but this time we're going to leave it in terms of e. So instead of y, I'm going to put in k. And again, a is 2. I'm using my formula here. You can simplify that down. That's perfect. We get e to the power of x is minus 2 over 2 plus e to the power of minus. Now, watch your signs here because it's minus 2 over 2. So the second e is going to end up with a positive power. So I'm going to simplify this down. So 2 over 2 is just 1. This simplifies to e to the power of minus 1 plus this turns into e to the power of 1. Now, they want that in terms of e, and you might think, oh, so I'm there. But actually, we would never leave our answer with a negative power. So what we're going to do is change that. We're going to use our rules of indices. So your rules of indices, they're in your log tables. We're on page 21. 1, 2, 3, 4. Fifth rule down on the left-hand side. A to the power of minus p is equal to 1 over a to the power of p. So what that becomes is 1 over e plus e. Now we can combine that using lowest common denominator. So we'll put this over e, but we'll also have to multiply the top by e so we don't change it. And we end up as 1 plus e squared all over e. Either line there would be accepted. So that part A, we had 3 very straightforward parts where all we were doing was subbing into the formula. The hardest thing we had to do was a little bit of work with our rules of indices. Now we get into maybe a more challenging piece. So this is asking us to show that or is the minimum point. So anytime we're talking about minimum or maximum in a function, we're going to be using differentiation. So what we're going to do is we're going to take our y, which is 2 over 2, e to the power of x over a plus e to the power of minus x over a. I'm going to simplify, sorry, that should be 2. I'm going to simplify this a little bit. So it's e to the power of x over 2 plus e to the power of minus x over 2. And what we're going to do is differentiate it. So we're going to do dy dx. So dy dx. Now, when we want to use our rules of differentiation, we're looking at page 25 of our log tables. I would suggest that anytime you differentiate that you have these open, because often I see students treat the e like we would usually treat an x to a power. It's not. So instead what we're using is on page 25, we're using the third and fourth rule in the box. So e to the power of x differentiates to e to the power of x, so no change. But e to the power of ax differentiates to a e to the power of ax. So really what's happening is the e part doesn't change. So this stays as e to the power of x over 2. But what we do is we differentiate this top piece. So this is a half x. So when we differentiate a half x, so this is what I'm looking at. So I differentiate this. This is the inner function. We're using a version of the chain rule here. When I differentiate x over 2, I'm effectively differentiating a half x, and I'm left with just a half. So we end up with a half e to the power of x over 2. So the e to the power piece, that doesn't change. All that happens is we end up with the coefficient, okay, which comes from the derivative of that power. Similar thing happens here. We still have e to the power of minus x over 2. That does not change. But we are going to again look at that inner function, which is the power, and we're going to differentiate that. So when I differentiate minus a half x, I'm left with minus a half. So that becomes my coefficient. So I'm going to tidy this up a little bit, and we end up with e to the power of x over 2 minus e to the power of minus x over 2 all over 2. And we can tidy that up even more if we wanted to, but remember what we're trying to do. Here we're trying to show that or is the minimum point. So to get my minimum, I take my dy dx and I let that equal 0. So what I end up with, multiplying both sides by 2, is I end up with e to the power of x over 2 minus e to the power of minus x over 2 equals 0. Now, these can be quite tricky to work with. So the first thing I'm going to do is I'm going to get rid of that negative power. So I get e to the power of x over 2 minus. This now becomes 1 over e to the power of x over 2 equals 0. Now, for most students, you'll find it easier to do a little bit of substitution here. So we let e to the power of x over 2 equal to something like, we have x, we have y, so and we've already had like an a, so we might use something like a z. So what we get is z minus 1 over z is equal to 0, and then we can work this through. So I'm going to multiply everything by z. So I get z minus 1 equals 0. I'm going to differentiate, or sorry, I'm going to factorize this. Z minus 1, z plus 1, because it's a difference of 2 squares. So I get z equals 1 and z equals negative 1. So once I have my two answers for z, what I'm actually going to do is go back to what we had. So we let e to the power of x over 2 equals z. So basically now we know e to the power of x over 2 equals 1, or e to the power of x over 2 equals negative 1. This is not valid because e is a positive number, and this positive number to any power, we can never make that a negative. So that one is not valid. For this one here, you can use logs, or we can use the idea that anything to the power of 0 is 1. So therefore, x over 2 must be a 0, because e must have been to the power of 0 to get 1. This means the only thing x can be is x equals 0. Okay, so I've worked that through to find x is 0, so that's where the minimum point happens. I now go back to my y. So y equals, we had this to e to the power of x over 2 plus e to the power of minus x over 2. I'm going to try find y when x is 0. So 0 over 2 plus e to the power of minus 0 over 2, which gives me y equals 2, which gives me the point 0, 2 as the minimum point, which is or, which is what we were asked to do. Now, if you want to use substitution, so when we got our dy dx, so this is kind of like an alternative way. So when you have dy dx, if you wanted to sub in x equals 0 and show that dy dx equals 0, all I would say there is just make sure that you check that it is a minimum point, that you haven't found possibly a maximum point. Now, I know we don't have a maximum point here, but when you just sub in, we need to be very mindful of this. So you might want to do a check on that second derivative. So check is the second derivative. For a minimum, remember that it is positive. So you want to check the second derivative is greater than 0. So part B, part 2, show by calculation that the slope of the tangent to the curve is always increasing from R to Q. So this is an interesting one, and it's quite tricky to understand what they're asking, but the maths behind it is quite straightforward. They're asking that the slope is always increasing. So if we were talking about the function itself increasing, we will be talking about slope. i.e. first derivative. But we're asked about the slope increasing. So what we want to show is the second derivative, when that is greater than 0, then it's increasing. Now, we want to show that it's always increasing, which means we want to show that the second derivative will always be positive. So let's start with our dy dx, which we had in a previous part, which is e to the power of x over 2. And I'm going to write that over 2 minus e to the power of minus x over 2 all over 2. We want to differentiate these a second time. We're going to use pretty much the exact same method as before. The e part does not change. This ends up getting multiplied by a half again, which ends up over 4. Here, same thing. We just end up now, so minus x over 2, that doesn't change. Again, we end up multiplying by a negative half because of the negative power. So this ends up as a minus 4. So this ends up as e to the power of x over 2 plus e to the power of x over negative x over 2 all over 4. So what I've done is I have changed the second fraction to a positive because it's minus and there's a negative at the bottom. Now, this will be greater than 0. Therefore, the slope of the tangent is always increasing. Now, that's fine and that's enough. But for you to understand, well, why? Why can we just say that this is greater than 0? Now, there's no need to explain it, but just make sure you're very clear about it. What we have here is e to a power. Again, go back to what e stands for. E is Euler's number, and it is 2.718, yada, yada, yada. And it keeps going on forever because it is an irrational number. But if you need to, your calculator has an e on it. So press e and equals, and you see that 2.718 and on. But basically what we have is a positive number, and it's to a power. Now, what a power means is multiply it by itself. So there's no way that if you take a positive number and you're multiplying by itself, it doesn't matter how many times you do that, it will never magically become negative, because a positive by a positive will always give a positive answer. So we're talking multiplication here. So that's why this is greater than 0. And you might go, but what about the negative power? Well, again, try that in your calculator. What is e to a negative power? Remember that a negative power, what it means, and if you want to go back to page 21 in your log tables, what it really means is a fraction. So that's 1 over e to a positive power, which again is still a positive number. It's small, it's a fraction, but it's still a positive number. So because everything here is a plus, so plus in the top line and the 4 underneath is a positive number, this will be greater than 0 no matter what value of x we put in, and therefore is always increasing. So the key really is making sure that you understand how do we show that the slope of the tangent, or that could be called the rate of change, is always increasing.